Hi, thank you for taking the time for our session, Model Monitoring. I'm Kaz, I'm developer advocate from Google Cloud. And with Mark Cohen, he's also a developer advocate for Google Cloud. And today we'd like to cover these topics. At first, I will introduce what is MLOps and how Google has been applying our MLOps practice for last 15 to 20 years. And also, I will introduce a product called Vertex AI for applying the MLOps practice in your production environment. And introduce a product called Model Monitoring, which is one of the most important products for applying the MLOps practices. And lastly, Mark Cohen will be showing a demonstration of the product. So what is MLOps and how Google has been applying that? And I have started talking about MLOps back in 2018, where I heard this word from one of the long-time software engineer, machine learning engineer at Google. He has been designing and operating one of the largest machine learning production system for around 10 years. And he said, launching the machine learning system is kind of easiest part. And the hardest part is keep operating that system for many years, like 5 years or 10 years. The real problem with the machine learning system will be found while you are continuously operating it for the 5 years, 10 years. So I thought this could be one of the biggest challenges for the industry in coming years. So this is the popular picture used in the MLOps talks. That is taken from the paper published by Google, where you have the machine learning code as a tiny fraction of the whole picture. So the data scientists could train a great model, machine learning model, but it could be a very small part of the whole production system that requires the different components like data collection, feature extraction, feature pre-processing, data verification, monitoring, analysis, and deployment, and so on. So this is all the challenges for the MLOps. But right now, in many enterprises and companies, there are a huge isolation between data science and IT systems. So I have seen a couple of the customers that in the POC phase, the proof of concept phase, the data scientists would be creating a nice, small, great model on the notebook, but they just pass it to the IT department, and the IT teams, the operation engineers would not understand anything what's happening inside the machine learning model. So even if they have some problems, they want to do some troubleshooting or monitoring, the IT department don't know what's going on inside the machine learning model. So this is the problem of the isolation. To solve these problems, so the practice of MLOps has been introduced in last 2 or 3 years into the industry. MLOps is all about unifying both of them. The development part by the data scientists and the operation part by the machine learning engineers or ops engineers. So this is the idea of MLOps. But it's not like, as simple as just bringing the DevOps practice into the machine learning system. It's not like that. So the DevOps problems could solve these challenges at the right side: scalability, availability, portability, those things. But in case of the machine learning systems, you always have to think about the challenges that is unique to the machine learning systems, such as the governance of data, features, models, pipeline, and so on. That means as long as you are starting to share the same features or models and pipelines with the many stakeholders or teams, you always have to think about the governance or the auditing of the artifacts. That is a unique problem for the machine learning. And also, you have to think about the continuous training pipeline. And we'll be talking deeply about the training serving skill later, and also data validation before start training the model, or after training, you have to do analysis on the model. And you also have to think about the machine learning fairness problem or explainability features. So those problems are unique to the machine learning systems and tightly coupled to the challenges in the DevOps problems. So this is the whole challenges we have for the machine learning MLOps. And we have been solving these problems for last 20 or 15 to 20 years. and published many papers that describes all the learnings and experience at Google. So this is how Google has been collecting all the knowledge about MLOps in the past. And now we have announced a new product called Vertex AI. That is the best platform for the customers and developers for introducing the same MLOps practice into their production systems. The Vertex AI is a managed ML platform for practitioners to accelerate experiments and deploy AI models. So basically, this is a shared platform for machine learning systems and development with the multiple roles and the stakeholders. Like a data scientist would be using the Vertex AI for the experiments and the development, whereas the ops engineers and the ML engineers would be using the same platform to looking at what's going on inside the machine learning pipeline and the deployment pipeline and the serving infrastructure. And also the other stakeholders like the product manager would be also sharing the artifacts, what's the latest, the accuracy of metrics with machine learning model, and to watch how the machine learning model is working well for getting the nice user experience. So there are many different ML ops challenges and ML life cycles. The Vertex AI is designed to solve these problems with the different components and services. And today I'd like to look at the 3 different problems: the continuous training, the feature management, and the continuous monitoring. And for each problem, we announced a new product called Vertex Pipeline and Vertex Feature Store and Vertex Model Monitoring. Vertex Pipeline is a product for defining your own pipeline for the machine learning lifecycle management. And this is based on the open source tool called Kubeflow Pipelines. And so anybody can take a look at the source code and run it on anywhere, even not on the Google Cloud. You can run it on your local environment or on-premise or other cloud. But the benefit you could get with using the Vertex Pipeline it's a serverless environment for running the Kubeflow pipelines. So you don't have to think about setting up your virtual machine or thinking about the cost of the virtual machines, shutting down and anything. It's automatically instantiated and it's scalable. So whenever you press a button to start running your pipeline design, then automatically it provides the computation power taken from the cloud pool. And you have to pay only for what you use. And in the Vertex pipelines, you have the user interface where you can easily define the pipelines and with your components. So you define the components. Inside the components, actually, you have the Python code you have written for the data ingestion or data preprocessing with Dataflow, or training with the PyTorch or TensorFlow or R or scikit-learn, anything. Data validation or model validation, and the deployment by pushing the model into the production. Any kind of the Python, the processing code could be encapsulated as a component and build the pipelines with the components. That's the pipeline, Vertex pipelines. And the one big benefit you could get with the Vertex pipeline is that you can track all the artifacts and the lineage between the data, feature, model, experiment, metrics, and so on. So what kind of the data set you have used, or what kind of the feature data you have used, what kind of the model design was used to train an actual models, what kind of the metrics you get with each experiment. Everything can be stored on the metadata store inside the Vertex pipeline. So all the stakeholders, not only the data scientists, but also the ML engineers or ops engineer, anybody can take a look at all the metadata stored in the past. So that allows you to have more high governance on the tracking and auditing against the production level, the model design and the feature data. That was the pipelines. The second product is the Vertex Feature Store. This is another product for sharing and reusing the machine learning feature data across many different use cases, like the experiments by the data scientists or serving at the production systems. as long as you are handling this feature data, the feature store could be very useful, the foundation for your ML ops practice. So, for example, one problem data scientist and ops engineer is facing is that it's not easy to build the online serving feature, online serving infrastructure for features. For example, if you quickly retrieve the user vectors by user ID or product vectors by product ID, you have to have a couple of the meetings with the ops engineers to build the scalable and available feature serving infrastructure by yourself. But you don't have to do that if you introduce a feature store. You can just, for example, data scientist would be creating some feature values like the user vectors or product vectors or anything, just throw them into the feature store. So the ops engineer could write some code to retrieve those features by using APIs. Those API can provide each features in very short latency. So you don't have to build the online serving infrastructure by yourself. And also by sharing exactly the same the feature values inside the shared store allows you to avoid the training serving skew. So you can avoid the situation where the data scientists and ops engineers are using two different implementations for producing the same feature values to avoid the skews. So that was the two products we have announced recently for the MLOps. And the third product is model modeling. So why we would need to monitor the models? So the problem is that in many cases, the machine learning models doesn't work well without any explicit signals or any alerts, because any models can get stale in time to time. So you have to define a freshness requirement based on your requirements of your machine learning model. For example, if you're training a voice recognition model, maybe you don't have to retrain the model for every day. Maybe the voice recognition model would work for a while, like 1 year or 2 years. But if you are training a recommendation model for the EC side, then maybe you want to retrain the model every day because you'll be getting the new products coming in every day. So that's how the model could be stale. And as long as you are not watching what's happening in the stale model, you'll be seeing the silent degradation of the performance or user experiments happening at the production system. And a major reason why you are degradation in the performance is the skew and drift happening in the production system. So this is one of the most important lessons we have learned at Google in the last 20 years. Skew and drift could be the silent killers of your machine learning models. What is skew? Skew is just like the situation where the data scientists will be training their machine learning model with the feature distributions for the green bananas, whereas the ops engineers are doing the same things with the feature distributions for the yellow banana. So they are thinking that they are doing the same thing, but in the reality, in many cases, there could be a slightest changes, like how implementing the same algorithms in their own code, or how you define the window in the time series, the analytics, or what kind of the changes you would have in the notebook environment and the production data warehouses. Every slightest changes could be introducing skews between the training and serving, so that the model could not be working well as intended. And what is drift? Drift is a skew for the time series data. So at the time of the launching, maybe your serving infrastructure is working well, but from time to time, the feature distribution could be changing from green bananas to yellow bananas, or maybe brown bananas. So that could be silently kill the performance of your application. So at Google, this quotation is kind of the very important practice we have learned. And we want the user to treat the data errors with the same rigor and care that they deal with the bugs in code. So in IT systems, in production, many people are writing tens of thousands of lines of testing code, unit testing code, or sometimes millions of unit testing code to make sure that your production system is working as intended. but are you doing the same things for the machine learning models? How do you validate the behavior of your machine learning model in productions? And many people are just watching the few numbers like the accuracy or AUC curve and so on. But accuracy number, the precision and recalls doesn't tell anything about all the possibles, the prediction result happening in the production. So data validation is the most important part for making sure that the model is working as intended. Actually, Google Play team was able to increase the overall average installation rate for all the mobile app on the Google app for the 2% after introducing the practice of data validation. So this is a huge impact for their team. So to reproduce the same success in your own environment, we have introduced the product called Vertex Model Monitoring. This is a tool for setting an automatic alert for your data scientists and ops engineers, ML engineers, whenever the model's performance changes. Actually, what it's doing is detecting the drift and skews happening in the prediction result, so that you can make sure that your model is working as intended with high reliability. And what it provides is some nice user interface, professional quality monitoring and alerting setup, where the ops engineers or data scientists can do some troubleshooting or diagnosing based on the visualization result. And you can also set up the model monitoring to trigger the retraining the whole pipeline. And you can do that automatically, or you can do that manually. You can choose that by defining your Vertex pipeline components. So whenever you get in any alerts of the detection of some skews and drift, it could trigger the retraining the model with the latest training data, so that it can automatically push the model into the production, or you can choose to use the human in the loop pattern, where any human operators or the directors or product managers are authorized to pushing the model into production. So especially for the training drift and skew detections, you can visually compare the skews as the bar charts. So you can visualize the two different distribution of the features. For example, this is the feature distribution with the data in the 1 month ago, and this is the distribution for the current data you are getting. So you can easily check out what's the difference of the distribution. And how to detect the skews and drift for each features. Actually, and for each skews and drift, we are using the two different divergence and distances. For the numerical features, we use the JS divergence and calculate the distance. And for the categorical features, we use the L infinity distance. And we provide the API for calculating those features based on the sampling result from the prediction result. So that was the introduction of the three products, and especially the model modeling. And now let's take a look at the actual demonstration of model modeling by Mark Cohen.
I'd like to give you a demonstration of model monitoring in the context of how someone might use it in the real world. Our story starts with a model, and the one I'm using comes from this very nice blog article that was written by a couple of my colleagues about a churn prediction task. The idea here is that your company sells a mobile game app, and you'd like to predict which users are most likely to churn, by which I mean abandon using your app. The business value in finding those users is that if you can identify those who are most likely to quit, you can try to reach out to them or provide some sort of incentives to increase their engagement. To solve this problem, we start with some Google Analytics data, which gives us demographic information like the player's country, environmental data like the operating system on the device they're using, as well as lots of behavioral data like which events they triggered and what count of those events as they were playing our game. Our next stop is BigQuery. The raw Google Analytics data is stored in BigQuery, which is Google's enterprise data warehouse. BigQuery makes it easy to view, analyze, pre-process, and train a model using standard SQL. So let me just show you what we have here. This view called train is the pre-processed information. So I've taken the raw Google Analytics data and sort of massaged it into a form that's readily usable to train a model with. You can see it has, here's the schema for the training data. It has all these event counts. It has timing information, the user's pseudo ID, the country, operating system and language of the user, and so on. Probably the most interesting field is down here, churn. That's an actual indicator. It's 1 or 0 to say whether that user indeed did churn or not. And so that's what we call the label in our labeled data set. And we're going to train the model to predict that value if it has all of the other information except that field. So how do we train a model in BigQuery? Actually, very simply use a statement like this. This SQL says create or replace this model, churn logreg. The model type is logistic regression. The label column, which we're going to use to define what the model predicts, is churned, and that corresponds to the field I just showed you in the schema. And then we're going to use the data from this train table. But let's say we want to use this model in a different context. All we have to do is click on the model, and over on the right we have an export model button where we can enter a Google Cloud Storage bucket, click submit, and then BigQuery will save all of the artifacts of our model in a reusable fashion into cloud storage. So this is Google's Vertex AI models page, and this is where we want to go in order to import the model that we just exported to cloud storage. So we'll click the import button. We'll give our model a name, tell it which region. And here we can either create a new container or have the service build a new container for us, or we can import an existing container. Given that, I'm going to tell it where to look for the model. mco-mm model, I think I called it. We select the framework and the framework version, and the other options here are scikit-learn and XGBoost beside TensorFlow. And then I'll go ahead and click import, and it will actually grab the information from cloud storage and create a new model. It takes a little bit, but not too long. Actually, there it is already now. And the next step is to go to the endpoints page, and to create an endpoint. You can tie an endpoint to multiple models and do traffic splitting and all that stuff, but we're going to use a very simple example where we're just going to go 100% to the model that I just created, and we'll create an endpoint called endpoint. We add the model that I called model. We can give lots of information about how we want the computing to be done. One required option is the machine type. We'll choose N1 standard 2, click continue, and then give it again the location and create, and now it's going to create an endpoint for us. This takes a little bit longer, but it's not too bad, and I've already done that for our model. The one I'm going to use in the further examples is called churn2. So next, let's go to a Jupyter notebook where I want to show you a different view of things. So this is a Jupyter notebook hosted on Google's Colab service, and essentially this will walk you through most of the things I'm showing you here in this demo so that you can try it for yourself. We'll share a link with you later on in the talk so that you can access this notebook. But what this really illustrates is the idea that almost everything in Google Cloud can be managed in any of three ways, really. The console web UI that I've been showing you, as well as the G-Cloud command line tool, and programmatically using any of our supported client libraries. And this notebook essentially does most of what I'm doing in this demo using a combination of Python code and the G-Cloud command. So I'm not going to go through the actual steps, but I will invite you to try them all for yourself. It basically has you set up a bunch of things to get started. Then it programmatically imports your model, the equivalent of what I just showed you. Programmatically then deploys an endpoint. So again, using Python to do those last two steps. This one I will run just to show you that we can run a prediction test directly from a Python client. So here's let me make this a little bit bigger. Here's the request, and as you can see, I've fabricated data so that it meets all the requirements for the model, and then I get a response. So this is live. It's telling me that the chance that this particular user of the game will churn is 0.87 and conversely 0.13 probability that they won't churn. So the predicted churn value is 1. It's telling us this is a likely churn candidate. So now that we're convinced that our model is actually responding to predictions, we want to monitor it. And the idea, as you've already heard, is to keep an eye on the model to make sure that we get notified if the data that's being sent to the model is deviating from over time or from the data that we use to train the model. So we specify some input for this modeling job, specifically an email address where we want to receive notifications, a sampling rate for how much of the log data we want to be examining, a monitoring interval, which I'm setting to 3,600 seconds. So once an hour, we're going to run this analysis job. In this case, we give it the schema for the training data. Sometimes the service can figure out automatically, sort of infer the schema. But in this particular case, the schema wasn't part of the artifacts that were imported, so we have to direct it to the BigQuery table I showed you earlier that captures all the schema information. And then I set a bunch of thresholds for drift and skew. So this is for things I want to monitor between training data and production data, as well as things I want to monitor over time as the model is serving traffic. And what will happen next is you'll receive an email at the address you specified informing you that your monitoring job has been created. Included in that will be some useful information down at the bottom, like the endpoint name, the job name, the monitoring job name itself, as well as a path in cloud storage to where it's going to store all your statistics and anomalies. The last thing I want to show you is how we can actually verify that the monitoring job is doing what we're expecting it to do. So this code, which you can access in the notebook, is essentially doing a load test. It's running repeated prediction requests with data that is closely aligned with the training data, with two exceptions. I've modified the mean and the standard deviation of one numerical value, and I've modified the distribution of one categorical value. And with that, we should be able to see that the model alerts to tell us that the training is skewing from the production traffic is skewing from the training data. And it should also identify which features are triggering the problem or exceeding the thresholds we've set. So this is a sample alert message. This came to my email, and it's basically giving me information about the model, the endpoint, the monitoring job, and which anomalies it detected. So it's giving me the actual features that exceeded the thresholds. And in this case, we're only seeing training and production skew because I ran a very short test. If I had run a longer test on the order of an hour or so, then I would also get drift anomalies triggered. And these alerts can also be viewed in the Cloud Console. So I'll show you that very quickly. If you go into the endpoints page, something that I don't think I pointed out earlier, but that I should have, you can actually see a new column here called monitoring, which will tell you whether a monitoring job is run or not, based on whether that says enabled or disabled. And then you get some performance metrics. You can see my load test running there. I get latency data, response distribution, and so on. And if I keep drilling into this, I can see a history of all the alerts, which features alerted, what type of alert. And again, lately I've been doing short load tests, so I've only gotten the training serving skew. But you can go back and get all the information about this, what the threshold was, when it fired, etc. So hopefully that gives you a sense of how to use model monitoring and what it can do for you and how well it's integrated with the rest of our Google Cloud Platform products. Thank you for watching.
Thank you, Mark, for the demonstration. So that was the quick introduction of the model monitoring. So now you have learned the 3 different products for the applying the MLOps MLOps practice into production. So if you're interested, please take a look at our product pages at cloud.google.com. Thank you so much.
The FairPrice Group was formed in 2019. Our mission and our vision is to service the Singapore society and to moderate the cost of living in all things related to food. Our food needs to be high quality, the supply needs to be pristine, and then our customer experiences need to be the best. Digital transformation is the present and future of our business because we need to constantly innovate and iterate to provide the best experiences for our customers here in Singapore.
In 2020, the key challenge for us for our digital transformation journey was driven by the COVID-19 pandemic.
We've adopted the use of new technologies. For example, the use of video conferencing and the sharing of documents in real time so that we can work at lightning speed to respond to the changing situation for Singapore. Google has been a tremendous partner, helping us gain better visibility in terms of data so that we can then tweak and change our processes to service our customers better.
Google Cloud offers us a platform where we can easily deploy some of the technologies that we are using today and have great native support for all the things we do.
Where there was the social distancing, we introduced new technologies such as Scan and Go that allow customers not to have to interface with other people in close contact, but rather to use the phone to scan the products and to pay with their mobile devices and then just skip the line.
We want to personalize our engagement with every single customer according to their preference and the needs. This requires us to do large-scale data analytics and machine learning to discover the customer insights and build recommendation systems. Google Cloud offers us a scalable platform to unify our analytics infrastructures to host all the available data sets around our customers.
In general, all these initiatives have helped us to become now the #1 online grocer as far as user ratings are concerned. Our partnership with Google has been strong, and I continue to see that take us to greater heights.